Howdy! In this video we're going to cover example 6.2. This is on static failure theories. Example 6.2 is asking us to calculate the safety factor for 5 different stress states based on the maximum normal stress theory, maximum shear stress theory, and maximum distortion energy theory. Now this is a neat example because it goes through various different scenarios regarding the different combinations between principal stresses that can occur in a stress state. So for example, here we have sigma 1 is positive, sigma 2 they're telling us that is 0. For case number 2, sigma 1 is positive, sigma 2 is compressing, so it's going to be negative. Sigma 3 has positive and negative, but now the values are the same. Sigma 4 has both sigma 1 and sigma 2 positive of 60 and 30, right? So case 1, 2, 3, and 4, we're working with principal stresses. Again, how do we know when we're working with principal stresses? Number one, at least in the book that we're using, anytime they designate sigma as sigma 1, that means it's a principal stress. But regardless of the notation that they're using, whenever you look at a stress state, like anyone here from 1 through 4, if all you see is normal stresses, if you never see any shear stresses, then it means those stresses are principal stresses. If we look at case 5, in this one we have no normal stresses, only shear stresses. So this would be the case for the maximum shear stress in that plane. And that gives, in this case, a tau of 60. The units that we're working with is megapascals. So again, what we're going to do is calculate the safety factor. If, for example, the material that we're using has a yield strength of 160 MPa, what's the safety factor based on all the different theories? Now the procedure that we're going to use to solve this problem goes as follows. First, we're going to draw the 3D Mohr circle. Once we have the 3D Mohr circle, we're going to identify what I call sigma max. You won't see this on the textbooks, but this is my way of saying that we're going to look at all the 3 different Mohr circles. And for the biggest one, we're going to look at the value of the principal stresses. And we're looking specifically for the biggest magnitude. We're also going to be looking at the tau absolute maximum shear stress. Again, this one's going to come from the biggest circle from the 3D Mohr circle. Next, we'll also calculate equivalent stress. This is a stress that we need for the maximum distortion energy theory. And then we're going to use all these values and we're going to plug them into the equation to calculate the safety factor. So here we go. Alrighty, let's start with the first one. Remember, the first step is to draw the 3D Mohr circle. So let's go ahead and look at the stress state that they give us. And it says that sigma 1 is positive 60. Let's go ahead and plot that point. So I have here already a little grid line. We'll put sigma, remember, and tau on the y-axis. Now let's plot 60. So 10, 20, 30, 40, 50, 60. So this is sigma 1 equal to 60. Sigma 2 is 0. So that's this point over here. This is sigma 2 equal to 0. Now, all the information that they give us is on this guy, right? There's no mention of sigma 3. So whenever sigma 3 is not mentioned, we can assume that that sigma 3 equals 0. Right? So sigma 3 equals sigma 2 equals 0. There we go. So now we have 2 points. We know that any of those 2 points lie on that circle. So this over here would be the diameter of the circle. If we want to draw a circle, we want to figure out the center and the radius. So where's the center point? In this case, well, we know the whole distance is 60. So half of that would be 30. So it would be right here. So that is the center of the circle. And it's at 30 and 0. What would be the radius? Well, it's going to be 30, right? Half of the diameter. So if I go 10, 20, 30 up, that's the radius pointing up. If I put the radius pointing down, it's going to be right there. What is this point, right? This is point, the sigma is at 30 and the tau is also at 30. So we have actually 4 points now. All of these lie on the same circle. So let me try to draw that circle. Here we go. Something like this. Like this. Oops. More or less. Anyway, so once we have the circle, what happened, right? We said 3D Mohr circle, I only have one. Well, actually there's two. This one in the blue is between sigma 1 and 2. Overlapping that circle is the one between sigma 1 and sigma 3. And then the circle between sigma 2 and sigma 3, and they're both equal 0, so it's just a point. It's not really a circle. Anyways, so now let's go ahead and calculate the safety factors. So the safety factor based on the maximum normal stress theory says that, well, the maximum normal stress theory says that if the maximum normal stress is equal to or greater than the ultimate tensile strength of the material, we're going to get failure. It also says that if the smallest or the most negative, let's say we had a point way over here. So if this stress over here is of the same magnitude or greater than the ultimate compressive stress, then we would get failure. The problem with this problem, or I should say the problem with this example, is they give us the yield strength. So remember your materials course. If we're plotting the stress, sigma, versus strain, the material behavior is first linear, then it starts deviating, it keeps climbing back up and then down, and then we got failure. Where the yield strength is somewhere over here, and the ultimate tensile strength is somewhere over here. Let's assume it's tensile, so SUT. Maximum normal stress theory wants us to use this value. However, when it's not provided, we can't just guess it. So instead, we're going to default to the next best guess, which is the yield strength. So again, we're supposed to use the ultimate tensile strength. When it's not given, the only value that we know is the yield strength. So that's the load that we want to design against, right? We don't want to exceed this one. So what that means is, oops, let me get this keyboard out. So we're going to use the yield strength, again, because we don't have the ultimate, and we're going to divide by the maximum stress. What is this maximum stress? Well, is this one here, which we just found. So on top, we put 160 megapascals. In the bottom, the stress was 60. So if we take 160 and divide by 60, this equals 2.67. So that's the safety factor based on the maximum normal stress theory. Next, let's do the maximum shear stress theory. Remember what that theory says? This one has us looking for the absolute maximum shear stress, right? That's the highest value of tau for any of the three circles in a 3D Mohr circle. And if that value is equal to or exceeds the yield strength of the material, then we get failure. So if we write the equation, the safety factor, up on top we want the shear yield strength, and at the bottom we want the absolute maximum shear stress. Now in this case, in this example, they don't give us the yield strength of the material. Well, they give us the yield strength of the material, but they don't give us the shear yield strength of the material. Oh yeah. Nonetheless, we know that whenever we're not given the value, we can estimate it by taking the yield strength and dividing by 2. So that's what goes up on top, and at the bottom, the absolute max. So as we put those values, the yield strength of the material is 160. We will divide by 2 to get the shear yield strength, or the strength of the shear strength of the material under shear The yield strength of the material under shear. Oh yeah, it's a tongue twister. Anyway, we take this value and we're gonna divide by the absolute maximum shear stress, which in this case we found to be at this point over here, which is 30. There we go. So if we type 160 divided by 2, which is really 80, and we divide by 30, we get a value of 2.67. And this is based on the maximum shear stress theory. Finally, let's do the maximum distortion energy theory. Remember what that theory says? The theory says that we have to calculate the equivalent stress, right? A stress that is causing about the same distortion. And if this equivalent stress is greater than or equal to the yield strength of the material, we got failure, right? So we can calculate the safety factor by just dividing the design overload, in this case the yield strength of the material, divided by the equivalent strength. So what is this equivalent strength? There's a couple formulas. We can look them up in the equation and reference booklet. One of them is this one here. When we know the principal stress is sigma 1 and sigma 2, then we can use this formula that says sigma 1 squared plus sigma 2 squared minus sigma 1 times sigma 2, and then the whole quantity raised to the 1/2 power. So if we plug in the values for this example, sigma 1 is 60 squared, sigma 2 is 0, minus sigma 1 times sigma 2. Remember, sigma 2 is 0, so we're not going to subtract anything. And then we're going to take the square root. So we're taking the square root of 60 squared. So in this case, the equivalent stress is just 60 megapascals. We can go ahead and substitute this value in this equation, right? So the safety factor becomes the yield strength, 160 divided by 60. And we calculated that number before, right, from the max normal, and that gave us 2.67. And this is the safety factor calculated following the maximum distortion energy theory. And as we look over our results for these calculations, we have 3 different failure theories, and notice they're all predicting the same safety factor. Interesting. Let's move on to stress state number 2 here. Let's look at what we have. They tell us that principal stress 1 is positive 60. Principal stress 2 has a magnitude of 30, but notice it's compressing, right? So in that case, this guy is negative. So let's go ahead and plot those 2 points. First one is 60, so it's going to put us over here. This is sigma 1 equal to 60. Sigma 2 is in compression, so it's going to be negative. So 10, 20, 30. This is sigma 2 equal to minus 30. These 2 points lie on a circle. That line that I highlighted is going to be the diameter, right? So the center of the circle is going to be somewhere in there. What the center of the circle is going to be? Well, let's take the whole diameter. So we got 60 plus 30, or 90. Right? When we take 90 and we divide by 2, we're going to get 45. So that means that the center is going to be 45 away from either of the 2 points. So we can go negative 30 plus 45, which is going to take us to 15. Or we can go 60 minus 45, which is going to take us to 15 as well. So the center point is here 10. 10 plus 5, 15. This is the center over here. The center is at 15 and 0. Right? Remember, our radius was 45. So if I draw a line straight up, 10, 20, 30, 45. Right? This is going to take us here to this, this point. is, sorry, I'm getting ahead of myself, hold on. So this point is gonna be a value of sigma of 15 and a tau of 45. If we draw the point at the bottom, 10, 20, 30, 45, it would take us over here. So let's go ahead and connect these points with some arcs so that we get a circle. More or less like this. So we have the circle between sigma 1 and sigma 2. There's no mention of sigma 3. So we assume sigma 3 equals to 0. So sigma 3 is here. I wanted green. That is sigma 3 equals to 0. So that means we can make a circle between sigma 3 and sigma 2, something like this, and one between sigma 1, which is 60, and sigma 3, which is at 0, something like this. They're not very neat circles, and I am not bothering to look or calculating specifically the center for each of those circles and the radius. Why? Because I can already tell, right, that the blue circle is going to be the biggest one. So that plane, this one that they gave us already, has the highest stress acting on it, right? So what is the max normal? So the highest value of the normal stress is this one here. So sigma max is 60. What is the highest shear stress? Well, we got 3 to pick one, right? We got one from this little circle, one from this next biggest circle, but the absolute largest shear stress is this one on the blue circle. So this is the absolute maximum shear stress. That one has a value of absolute max of 45. So with these two values, we can go ahead and calculate the safety factor. So safety factor for max normal is going to be 160 divided by 60. So we plug this in the calculator, we get, let me see, 2.67. We've done this one before. If we calculate the safety factor for max normal, remember, we're going to take the yield strength and we're going to divide by 2. And then in the denominator, right, we put the absolute maximum shear stress, which is 45. So we plug this in the calculator, we get 1.78 for max shear. Next, for maximum distortion, we have to calculate the equivalent stress. Remember, this equation is sigma 1 squared plus sigma 2 squared minus sigma 1 times sigma 2, the square root of the whole thing. So the values are of sigma 1 squared is 60 plus negative 30 squared minus 60 times minus 30 square root of the whole thing. So when I plug this into my calculator, hopefully I didn't make any mistakes, I get a equivalent stress of 79.37. So with that number, I can go ahead and calculate the safety factor. Remember, we never want to exceed the yield strength of 160, and the equivalent stress is 79.37. So if we type this on the calculator, you can see the answer is going to be very close to 2. So this equals 2. If I'm specific, 202 safety factor. So this one we can see we applied the 3 different theories. We have factors going from 2.67, 1.78, and 2.02. So when asked like which one is a better predictor, if we assume this is a ductile material, right, we would go always with the maximum distortion. So around 2 is the better predictor for the safety factor. Let's go ahead and move to number 3, or stress state number 3. What do we have over here? We have sigma 1 of positive 60, sigma 2 of negative 60. So let's go ahead and plot these points. So positive 60, 10, 20, 30, 40, 50, 60. This is sigma 1 of 60. Sigma 2 is compression, right? Oops, sorry. They don't tell us it's a negative number, but by looking at the direction of this arrow, we see that it's compression. So this will take it to minus 60. Oops. So 10, 20, 30, 40, 50, 60. Yes. This is sigma 2. And it's a minus 60. So those 2 points lie on a circle, right? That yellow line is the diameter. We can calculate the center very easily, right? Because we have plus 60 and minus 60. So the center for that circle is right over here at 0, 0. That's that center. And what is the radius? Well, the radius is just 60. So if I go up the radius, 10, 20, 30, 40, 50, 60. And if I go down, 10, 20, 30, 40, 50, 60. Right, that circle has to connect all those points. So let me see if I can connect them real quickly. And when you're making the circles, you don't have to be like super precise. We're not getting points like graphically, right? We can use the formulas. So it's just to paint a better picture. Anyways, so here we have the circle from this one. Remember, when they don't mention sigma 3, that means sigma 3 equals 0. So we have sigma 3 right at 0, which means we can now have the other 2 more circles, right? Between sigma 1 and sigma 3, which is at 0, we will get something like this. And between sigma 2 and sigma 3, something like this. When we look at this one, it's very easy to identify which one is the highest value of sigma. Well, we have positive 60 and negative 60, right? So the biggest magnitude is 60. So sigma max is 60. Remember, when we're talking about the max normal, the maximum stress expected, which in this case is 60, cannot exceed the ultimate tensile strength. If we're talking about this point, the positive one, right? If for some reason sigma 2 was maybe negative 90 and sigma 1 was 60, so if sigma 2 was way over here, then this would be the biggest value, and we would use the 91. And ideally, you would want to be using the ultimate compression strength of the material. So just a heads up. In this case, sigma 1 and sigma 2 have the same magnitude, which is 60, right? So, and since we don't have the ultimate tensile strength, we're going to go ahead and just use the yield of 160. So this number we've calculated before, that safety factor is going to be 2.67 based on the max normal. Now the max shear is going to have us looking for the biggest value of shear stress, right? So we have one from this circle, one from this other one, but the absolute biggest one is from the biggest circle, which is this guy. It's absolute max. What is the value of this one? Remember what it is, right? This one lies on that blue circle. The radius was 60. Okay, so then we can calculate the safety factor. The safety factor for the maximum shear stress says that the maximum expected shear stress, which in this case is 60, cannot exceed the shear yield strength of the material, right? Which we can approximate by taking the yield strength of the material and dividing that by 2. So if we plug this on the calculator, we get a value of 1.33 for the max shear. Next, for the equivalent, you already know, right? By now, hopefully, we have to use that formula. They give us principal stresses. So the formula is sigma 1 squared plus sigma 2 squared minus sigma 1 times sigma 2, the whole quantity to the 1/2. What is the value of sigma 1? Well, sigma 1 is positive 60 squared. Sigma 2 is negative 60 squared minus positive 60 times negative 60. Everything to the 1/2 power. If I did not make any mistakes on this one, I am calculating the equivalent strength to be 103.92 megapascals, right? We can use this value to calculate the safety factor. Safety factor says that the normally expected load, which is 103.92, cannot exceed the yield strength, which is 160 for this material. So if we plug this on the calculator, we get a value of 1.54 for this safety factor. Let's move on to stress state number 4. Here we go. So what does stress state number 4 tell us? We have a sigma 1 of 60 and a sigma 2 of positive 30. So let's go ahead and plot these points. So 1 here is at 60. That's the sigma 1. Sigma 2 is at 30, 10, 20, 30. Right there. These 2 points lie on a circle, right? So that's our diameter. What's the center for that one? Well, it's going to be right smack in the middle. So from 30 to 60, it's a distance of 30. We divide by 2, that's 15. So if I add those 15 to the 30, it's going to take us right there, right? So this is 30, 40, 45. And that radius was 15. So it means if I go 10, 15 above, 10, 15 below, right? We have 4 points that all of these lie on the circle. So let me go ahead and connect them. 1, 2, 3, 4. Something like this. Again, this was for sigma 1. This was for sigma 2. Where is sigma 3? Well, sigma 3, if there's no mention, we assume as 0. So that means over here we have sigma 3 equal to 0. What that means for us is, hey, we can make a circle between sigma 2 and sigma 3. So something like this. It's actually the same size as that blue circle. And then we can make another one between sigma 3, which is 0, and sigma 1, right? Which would put the diameter all the way over here, right? The center of that one, that circle, is going to be right at 30, which means the radius is going to be 30, 10, 20, 30. If I go down 10, 20, 30, so let me try to connect these points, something like, oh yeah, like this. Right? Once we have the 3 more circles, it's very easy to see or to pick up which one has the highest value for the sigma. Or sigma is going to be highest right here. So the max in this case is 60, right? Where is the shear stress highest? Well, it's going to be on the highest circle, right? Not this one, not this one, but this one over here. And that's the value we'll use for the max normal. So tau absolute max in this case was 30. Okie dokie, let's calculate some safety factors. Maximum normal says that the maximum stress expected, which is 60, cannot exceed the ultimate tensile, or in this case the yield strength. So we got 160 divided by 60. This is going to give a safety factor of 2.67. when we look at the maximum shear stress, right, the safety factor says that the absolute maximum shear stress, which in this case is 30, cannot exceed the shear yield strength of the material, which is just the yield strength of the material divided by 2. So we put this on the calculator, we get a number of 2.67 for max shear. Lastly, let's calculate the equivalent stress, right? Remember the equation is sigma 1 squared, so in this case 60 squared, plus sigma 2 squared, which in this case is 30, minus sigma 1 times sigma 2, everything to the 1/2 power. So if I did this one correctly, I'm getting that the equivalent stress is 51.96. So armed with this value, we can calculate the safety factor, right? Maximum distortion theory says that the equivalent stress, which is 51.96, cannot exceed the yield strength of the material, which is 160. So if we take 160 and divide by 51, we get roughly 3.08. There we go. One more to go. We go ahead and move it so that we get some space. So stress state number 5 has a tau value. There are no normal stresses here acting, right? So this stress state is already the state for the maximum shear stress, right? But don't let that scare you. We can still make Mohr circle. So what do we have over here? Well, we know that the shear stress is 60. We can make a plot, right? So remember, normally we're plotting values of sigmas and tau. What is the value of sigmas here? Well, they're 0, right? So I'm going to start at 0. And I'm going to have the shear stress of 60. So this can either be up, positive, 10, 20, 30, 40, 50, 60. So right there. Or negative, 10, 20, 30, 40, 50, 60. Right? So in this case, the diameter of the circle is like this. We got those 2 points. They lie on that circle. Sigma is 0. Right? So there we go. So what is the center of that circle? Well, the center is the origin. What is the radius of that circle? Well, the radius is 60. So I can go ahead and move the radius now here to the, not move, right, but project it to the right, project it here to the left. And there we go. Right, we got 4 circles. I'm going to try to connect them as best as possible. 4 points. I'm going to connect them so I can make my circle. Here we go. So this is the circle that we have. Remember, this orientation as given is this one here. But if we change the orientation of this guy 45 degrees, which is on the Mohr circle is 90 degrees, we're going to be at these points over here. And then lastly, remember, they give no mention of sigma 3, principal stress 3. So we'll assume that the sigma 3 is going to be 0. So we have another point there, which means now we can make the other 2 Mohr circle. One between sigma 1 and sigma 3, and the other one between sigma 2 and sigma 3. Still, we want to draw these, right? We have the Mohr circle. We want to look at the biggest one, and we want to ask what is the highest value of the sigma. Well, it's going to be either this point or the other one. They have the same magnitude, so the sigma max is 60 in this case. What is the maximum value of tau? Well, it'll be this guy here, right? Absolute max, which is also 60. So we can plug all of that into our equations, right? The safety factor for the max normal says that the sigma max 60 cannot exceed, in this case, 160. So 160 divided by 60 gives us 2.67. Next, if we take the safety factor for the maximum shear stress, they're telling us that the absolute maximum shear stress expected, which is 60, cannot exceed the shear yield strength of the material or the yield strength divided by 2. So this one's going to be 160 divided by 2 divided by 60, which gives 1.33. And finally, let's calculate the equivalent stress. Well, what is sigma 1? 60 squared. What is sigma 2? Negative 60 squared minus 60 times negative 60, and then all of that to the 1/2. If we plug all of that into the calculator, we get an equivalent stress of 103.92, which we then can use on the safety factor, right? Remember, the equivalent stress, 103.9, cannot exceed the yield strength of the material, or 160. So 160 divided by 103.9 gives a safety factor of 1.54. And there you go. We've completed. This is the fifth stress state. And we practice, again, drawing the Mohr circle and applying the maximum normal, maximum shear, and the maximum distortion energy failure theories. I want to remind you that every time that we were looking at the stress states, right, we were working with principal stresses, sigma 1s and sigma 2s. But it's not to say that if we give you sigma x and sigma y that you can't necessarily just plot those stresses. Still draw the Mohr circle and figure out the principal stresses and the absolute maximum shear stress, all of that. Anyways, I hope you found this video useful. If you have any trouble with it, meaning you have any questions or you found out a mistake on my math, do let me know in the comments down below. Otherwise, we'll see you on the next one.